The idea behind that is that when we do any exercise, we switch on signals, molecular signals in our muscle that respond to some sort of contractile stimulus. It might be an endurance stimulus, it might be a resistance stimulus, but we're switching on these like pathways, if you will, that when you repeatedly switch these proteins on and these signaling pathways, they are involved in promoting specific adaptations. So in the case of endurance exercise, some of the classic ones that are studied is like AMPK, P53, PGC1 alpha. These are all like, targeted genes and proteins that when they're repeatedly stimulated over time, they switch on this kind of process that leads to improvements in like mitochondrial biogenesis, where we increase the number and the function of our mitochondria and other like angiogenesis and other structural and functional adaptations that promote endurance adaptations. And with resistance exercise, I mentioned before, the mTOR pathway is a classic studied pathway that's stimulated by resistance exercise that promotes protein synthesis. And when we're repeatedly stimulating that pathway, we get an increase in muscle proteins. And so there's this idea from a molecular point of view that one pathway might interact or interfere with another. And a lot of this evidence comes from cell culture studies and studies in rodents. So there's another classic one that was by Phil Atherton back in 2005, where they basically stimulated rodent muscle with an endurance type stimulus. So very low frequency but prolonged stimulations, and then a resistance type stimulus, so really high frequency stimulation. And then they looked at like the pathways that were switched on. And what they found is that when you stimulate the muscle with an endurance type stimulus, it switches on this AMPK mitochondrial type signaling pathway. And when you switch on the resistance when you give a resistance stimulus, you then get this switching on of the mTOR pathway. And so it kind of brought up this idea of that, when you do one, you're going to downregulate the other and vice versa. And that, concurrent training may induce a negative molecular environment for your muscles to adapt. But in humans, first of all, again, there's very few studies that have kind of explored this. But there's very little evidence in humans to suggest that this is happening. And in fact, there's studies showing concurrent training can initiate similar, if not greater, signaling responses in the muscle. So very different to what we see in these like very tightly controlled cell culture and rodent studies. Like when we look at humans, there's a lot more variation, and there isn't enough conclusive evidence to say that there's this molecular interference effect.